Bombs away, a phrase synonymous with destruction, with unleashing immense power. We often associate it with military might, with fighter jets soaring through the sky, delivering their explosive payloads. But what if the target wasn't a military installation, or a strategic asset? What if, instead, the target was metal tubes? Sounds odd, right? It certainly raises an eyebrow. Why would anyone dedicate resources, potentially even military force, to eliminate something as seemingly innocuous as metal tubes? Imagine a top-secret operation, shrouded in secrecy, with classified documents detailing every step. A mission so sensitive, its very existence is known only to a select few. This isn't a mission for weapons or spies, no cloak and dagger stuff here. It's not about gathering intelligence or deploying cutting-edge weaponry, but for a shipment of metal tubes. A seemingly mundane cargo transported in ordinary shipping containers, yet possessing a significance far beyond their simple appearance. These aren't plumbing supplies, they're not the kind of pipes you'd find in your home or at a construction site. They're at the heart of a global puzzle. A complex web of international relations, geopolitical strategies, and the ever-present threat of nuclear proliferation. The potential creation of a nuclear weapon. The very thought sends shivers down the spines of world leaders and security experts alike. Why target something so ordinary? What makes these seemingly unremarkable objects so crucial that they warrant such drastic measures? Because these tubes are the key to a device, a sophisticated piece of machinery with the power to reshape the world, that can either power a city or destroy one, a dual-use technology capable of providing clean energy or unleashing unimaginable devastation. The story of these tubes is a real-life science thriller, a narrative filled with suspense, intrigue, and the constant threat of global catastrophe, where the smallest details can change the fate of nations, where a seemingly insignificant component can alter the course of history. To most, they're just metal, simple, unadorned, and easily overlooked. But to experts, their precise design screams nuclear ambition. The subtle nuances in their construction reveal a hidden purpose, a clandestine objective. The decision to destroy them shows just how high the stakes are. It's a testament to the gravity of the situation, a clear indication of the potential consequences. Our mission, uncover why these tubes matter so much, to delve into the science, the politics, and the potential dangers they represent. What makes a hollow cylinder a linchpin in global security? How can something so simple hold such immense power? The answer lies in the gas centrifuge, a marvel of engineering, a machine that harnesses the power of centrifugal force, a machine that spins at the center of nuclear science and international politics, a device that can enrich uranium, the fuel for nuclear power plants and, unfortunately, nuclear weapons. Let's dive in and see how a simple tube can tip the balance of power, how it can become a pawn in a high-stakes game of global chess. Science is the key to this mystery. Understanding the principles of nuclear physics is essential to unraveling the truth behind these metal tubes. So, what is this secret device we're talking about? What makes it so crucial, so heavily guarded, and so vital to national security? It's a gas centrifuge, a marvel of engineering, and a key component in the process of uranium enrichment. Think of it as a supercharged salad spinner, but instead of drying your greens, it's performing a far more complex and critical task. Except instead of lettuce, it spins uranium gas, specifically uranium hexafluoride. This is where the magic, or perhaps the danger, begins. The ultimate goal? To separate two nearly identical uranium isotopes, U-235 and U-238. One is just a tiny bit heavier than the other, but that slight difference is everything. Spinning at insane speeds, far faster than any kitchen appliance could ever dream of, the heavier atoms, the U-238, move outward, pushed by the immense centrifugal force. Meanwhile, the lighter ones, the U-235, stay closer to the center, congregating towards the axis of rotation, but the difference in weight is incredibly tiny, almost imperceptible, so you need not just one but thousands of centrifuges working in perfect synchronicity. Linked in cascades, a complex network where the slightly enriched output of one centrifuge becomes the input for the next, to get enough separation to produce enriched uranium, suitable for nuclear power or potentially something far more dangerous. Each metal tube is the heart of a centrifuge rotor, the core component where this isotopic dance takes place. Built from ultra-strong, specialized materials like miraging steel or carbon fiber composites to survive the immense forces inside. So, if a country suddenly wants to import thousands of these specialized tubes, it's a major red flag, a cause for serious concern and immediate investigation. They're almost certainly not planning a massive salad-making operation. That's precisely why intelligence agencies around the world keep such a close watch on these shipments, tracking their origin, destination, and purpose. Because these seemingly innocuous tubes are often the first clue, the initial thread in a much bigger and potentially very dangerous story. To understand the fuss surrounding nuclear materials and the debates that rage around them, we need to delve into the heart of the matter. It's a story of elements, isotopes, and the incredible power locked within the atom. So let's meet uranium's two key isotopes, the players that define its role in both energy and global security. These two forms of uranium dictate whether it becomes a source of clean power or a devastating weapon. These isotopes are U-238 and U-235. They're like siblings, sharing the same family name but possessing vastly different personalities. U-238 is the elder sibling, common and stable, making up over 99% of all natural uranium found in the Earth. It's the reliable, steady presence in the uranium family. Now, U-235 is the younger sibling, rare, comprising less than 1% of natural uranium deposits. But despite its scarcity, it's the superstar of the uranium isotopes. Why all the hype? Because U-235 is fissile. Its atoms are unstable and can be readily split, unleashing a tremendous amount of energy in the process. When you split one U-235 atom, you get more neutrons released, which then go on to split more atoms, creating a self-sustaining chain reaction. This is the key to nuclear power and, unfortunately, nuclear weapons. Control that chain reaction carefully and you have a nuclear power plant generating electricity for homes and businesses. But let it run wild and uncontrolled and you have a devastating atomic bomb. Nuclear power plants need uranium enriched to about 3 to 5% U-235, resulting in a slow, steady, and manageable burn. On the other hand, weapons need uranium enriched to 90% U-235, leading to an instant, massive, and catastrophic explosion. So, what's the only real difference between these two applications? The concentration of U-235. And that's precisely why uranium enrichment is such a sensitive process and is so closely watched by international agencies. Because the same underlying technology can be harnessed to light up a city, providing clean and reliable energy, or, in the wrong hands, be used to destroy it completely. Given the potential consequences, the stakes in the world of nuclear materials couldn't possibly be higher. Ultimately, it all comes down to how much of that special fissile isotope, U-235, you have and what you intend to do with it. Now let's see how this plays out in the real world, specifically Iran. Iran says it wants nuclear power, not bombs, but the same centrifuges can make both. Secret facilities, restricted inspections, and traces of enriched uranium have fueled global suspicion. The US and its allies responded with sanctions, negotiations, and even cyber attacks like Stuxnet, which wrecked Iranian centrifuges. The game Iran insists on its rights, others fear a hidden weapons program. The stakes, global security and trust. The heart of the controversy? The purpose of those metal tubes. Iran claims it's about energy independence and their right under international law. The West sees a threat. The same tubes could be used for bombs. Iran points to double standards. Why can others have nuclear tech, but not them? The US and allies cite secrecy and missile programs as reasons for mistrust. For one side, the tubes mean progress. For the other, potential catastrophe. That's why this debate is so explosive. Let's get technical. You can't spin solid uranium, you need uranium hexafluoride gas. This gas goes into the spinning metal tube, where the rotor hits over 100,000 revolutions per minute. The heavier U-238 is flung outward, the lighter U-235 stays closer to the center. Temperature differences create currents that help separate the isotopes even more. Tiny scoops at the top and bottom collect slightly enriched and depleted gas. The enriched stream moves to the next centrifuge, repeating the process thousands of times. Gradually, you boost U-235 from 0.7% to 5% for power, or 90% for weapons. It's a marvel of engineering, but also a potential danger. That's why every tube, every cascade is watched so closely. The line between peaceful and military use is razor thin. Why does this matter to you? Because nuclear proliferation is a global threat. Centrifuge technology is small, efficient, and easy to hide, making secret bomb programs possible. More countries with nuclear weapons means more risk of disaster by accident or design. Treaties, inspections, and diplomacy are our best tools to manage this danger. When trust breaks down, the world gets less safe. The story of Iran's tubes is just one example of a worldwide challenge. Science and technology aren't good or evil, it's how we use them that counts. Understanding the basics helps us make sense of the headlines and the stakes. The quest, keep these tubes spinning for light, not destruction. It's a science lesson with real-world consequences.